really struggle with is solving sinusoidal applications. So I thought I'd take a look at one today. We have a population of rabbits that's oscillating 25 above and below an average of 129 during the year, hitting the lowest value in January, which we're calling t equals 0. And here's the question. Find an equation for the population P in terms of the months since January T. All right, so one thing that helps me in finding equations is to maybe sketch out the situation on a graph so that I can visually see what's going on. So I'm going to sketch in a vertical axis and a horizontal axis, and I'm going to go ahead and label those. My horizontal axis, it says T equals 0 is January. So that represents months. And my vertical axis, it says, is P, which is the population. All right, now what else is given to me? The rabbit population is oscillating 25 above and below an average of 129. So let me go ahead and just draw in 129. Now remember, this is just a sketch, so if I was going to do a formal graph, I probably wouldn't actually call out 129. I might label my population axis maybe in increments of 20, so I would estimate where 129 is. But just for a sketch, I'm going to go ahead and put that 129 in there. So 129 is my average, and then if I go 25 above and 25 below, I see the highs and the lows. So if I take 129 and I add it to 25, what does that put me at? That puts me at 154, I think. And if I go 25 below, that would put me at 104. So I know that my highest rabbit population will be 154 and my lowest will be 104. Now what I also know, and I'll just switch to green, get a different color, is that January, t equals 0, it says I'm at my lowest value. So at 0, the origin, I am at the point 104. And in fact, I also know that this graph is sinusoidal, so 12 months later, I'll go ahead and put a 12 there, hitting January again, I'm going to be back at that 12. So my lowest is occurring at t equals 0, and then I see that t equals 0 again after 12 months. Now, because this is a sinusoidal function, what I know is that halfway between 0 and 12 months is 6 months, and if the lowest is occurring at 0 and 12, then the highest must be occurring at 6. So I'll go ahead and graph that in. What's really nice about sinusoidal functions is that because of the symmetry of the unit circle, there's a lot of things that I can say are true just basically off of that symmetry. Halfway between 0 and 6 is 3, and halfway between 6 and 12 is 9. All right, so I'm going to go ahead and sketch in this estimate. Again, remember, this is a pretty good graph. I've done a good job of labeling. But maybe you remember from previous classes that if your increments aren't uniform on an axis, you can put these lightning bolts there. So I could do something like that if I wanted to. All right, so what is the equation of this curve? Let's start with identifying a few things. What is the midline, I might ask? The midline, or the vertical shift, looks like that's happening at P equals 129. So in other words, we're taking an average that may have been at 0 and we're shifting it up to 129. From that midline, we have a difference of 25. So I'm going to call that the amplitude. The period of this function, how often is it repeating? It looks like it's repeating every 12 months. And so to find my argument for the inside of my trig function, I say that's 2 pi over b, where b is my argument. If I cross multiply this, I'm going to get 12b equals 2 pi. Divide both sides by 12. I'm going to get 2 pi over 12, which is pi over 6. All right, so I've got a lot of good information here. The last thing I want to talk about is, what does this look like? Does it look like a cosine function, or does it look like a sine function? Well, of course, we know sinusoidal functions can be either, depending on whether or not you have a shift. If we want to make this as simple as possible for ourselves, then we might just say that this looks like a cosine function that has been reflected. In other words, normally at t equals 0, for a cosine function, we would see it at its highest point. This one's occurring at its lowest point. So I'm going to say p of t is equal to negative my amplitude times the cosine of my b value, which is pi over 6. Now there's no shift on this one, so I'm just going to close off that parenthesis or close off that argument. And then I'm going to put my midline here, which is plus 129. So that is the function or the equation that models this scenario. The second part of this question says, what if the lowest value of the rabbit population occurred in April instead of January? How does this change the graph and therefore the equation? So I went ahead and took a screenshot of what we had done on the previous problem so that we could maybe have a better feel for what's going on here. The picture that we have, the graph in green, that is a minimum in January. Now what it's saying is that that minimum is not happening until April. So let's see, April is what month? Of course, we know it's the 4th month in the year, but let's just make sure that if January is t equals 0, then February is t equals 1, March is t equals 2, and actually April is t equals 3. So you want to be careful about how things are defined. Yes, April is the 4th month of a calendar year, but in the way that we've defined it, January is not t equals 1 like it is on a calendar. January is t equals 0 in this scenario, so April is t equals 3. So going over to the graph, instead of hitting that low point of 104 at 0, I would be hitting that low point at 3. So the graph has done what? The graph looks like it has shifted. And if it shifts to the right for that first point, then it's going to shift to the right for every point that follows. So I would see a maximum occurring after 9 months after t equals 0. And then it looks like I might have to add, let me see, I'll add a 15 down here because that's when it would hit its low. So that would again be April, but 12 months later. All right, so how does this change the graph? It shifts the graph 3 units to the right. Okay, now how does that affect this equation? We know that things that happen to the horizontal axis affect the argument, the inside piece. And we also know that what happens to that inside piece is that it does the opposite of what you might think. So what I mean by that is we would have P of t equal to negative 25 times the cosine of pi over 6. And now I'm going to put parentheses and show that shift. I'm going to the right 3 units, and so I'm going to say minus 3 plus 129. So that would be the effect of changing the lowest value to April instead of January. All right, and the final part of this question says, going back to the original function, so this is what we came up with on part A. Actually, that doesn't look quite right. What we had was negative 25 cosine of pi over 6t plus 129. That's what we wrote if you go back in this recording. Are those the same? They are. The reason why I typed it out this way is because typically what you're going to see, if possible, is that leading terms are preferred to be not negative. And so putting that 129, which is a positive value, up front is preferred. So we just use the commutative property and we reverse the order of those two terms. All right, so the question now is, after how many months, okay, so we're going to be looking for how many months, we're solving for t, will the population of the rabbits first reach 150? So the population reaching 150, that's a p-value of 150, and I want to solve for the months, which is t. When does it first reach 150, and then when will it reach this population again within a 12-month period? So in other words, within one period. We can do this algebraically, but it might help us to take a look at a graph first. So let's do that.
All right, one way that you can see the solution to an equation using a graph is by setting one side of the equation equal to y. So we had 150. I'm going to say y equals 150. And then have a second equation that's set equal to the other side. So we had y equals 129 minus 25 times the cosine of pi over 6, and it was t, but I'm going to use x because Desmos recognizes that pretty nicely. All right, and you notice there is nothing on my picture. If you remember from the sketch that we did, this thing has an average of 129, so we're not even seeing 129 on the vertical axis. So I'm going to go to the graph settings here, and I'm going to change the y-axis to something bigger than 129. And actually, I know it's 129 plus 25, so let me just put 160, and there it is. And then I'm interested in the time period for the first 12 months, so maybe I'll just go out to 15 and take a look. And let me make this darker so you can see it. All right, so there is the graph. Oops, let me go back to this. X-axis, I think I typed that in wrong. Let me go 15, how about that? 15, there we go. All right. So the red line represents y equals 150, and the blue curve represents the cosine function. And if I click on this, I can see that within the first 12 months, where these equations are intersecting is at 4.905 and at 7.095. So that's what I'm going to expect to see as an answer when I go and solve this algebraically.
Okay, so now that we've seen the graph, we have an expectation of what the solution should be. We should be seeing a population of rabbits reach 150 after 4.905 months, and then a second time after 7.095 months after January. So how do we algebraically do this? Well, let me go ahead and set up my equation. I'm going to say 129 minus 25 times the cosine of pi over 6t, that equals 150. And I'm going to begin the process of solving this for t. I'm going to try to isolate the t variable, just like we would in any other type of situation where we're solving. In order to get that t by itself, I need to get the cosine by itself. So I'm going to subtract 129 from each side. And when I do that, I get negative 25 times the cosine of pi over 6t equals, let's see, 150 minus 129 is 21. Just a side note here, sometimes students make the mistake of doing this subtraction. Order of operations says we always have to take care of multiplication before we do any subtraction. So this problem is actually not subtracting the 129 and the 125. This 25 is connected to the cosine of pi over 6t. We cannot combine that with the 129. They are not like terms. All right, so now I'll divide both sides by negative 25, and I get cosine of pi over 6t equals, and I'm just going to leave this as negative 21 over 25. I try to use exact numbers as much as I can. Okay, so I've almost got the t by itself. The next thing that I need to do is take cosine inverse of each side. So cosine inverse of the cosine of pi over 6t equals cosine inverse of negative 21 over 25. Now, when I do that on the left, the cosine inverse and the cosine undo each other. So this is nice. I'm now left with pi over 6t equals, and I'm going to put into my calculator cosine inverse of negative 21 over 25. And when I did that, it gave me approximately 2.568. Now I'm going to write 2.568, but it's actually 2.568079549, and it just keeps on going. Even though you see me write 2.568, I've got my calculator near me, and I'm going to be using the exact answers in the rest of my calculations. I'm not using just the 2.568. Now, here's one thing that you have to remember. There's another possibility here. If you think about what just happened, we said something like, what angle produces a negative cosine? If you go back to what the unit circle tells us, the unit circle tells us, that's a bad graph, but you get the idea. We can expect a cosine to have a negative value over here. So maybe in the second quadrant, maybe in the third quadrant. This 2.568 represents a radian measure. Now, what we know is that pi is 180 degrees and pi is about 3.14. Pi over 2 is up here at the top. That is 1.57. So I would estimate that a radian measure of 2.568 is somewhere in this second quadrant, 2.568. So the reason why that's the answer is because, yes, we do see, right, negative cosines. But we also see a negative cosine here. Now, what is that value? Well, you should have learned at this point that whatever your calculator gives you for cosine, that you can find additional answers either by using reference angles and using the picture that I just drew, or you can always use 2 pi minus whatever the calculator gives you. So when I put that into my calculator, remember I'm using exact values, 2 pi minus that 2.568079549 gave me approximately 3.715. Now, neither one of those answers is what I see in the graph, but I'm not done, am I? I'm going to go through now and I'm going to multiply each side by 6 over pi because, oops, that will get me the t by itself. So on the left-hand side, I'm left with t equals, and if I put all of this into my calculator, I got a t value of, I think, 4.9046700654. Rounding to three places, that'd be 4.905, and that makes me really happy because there it is in our graph. Let's hope that this second calculation gets me the 7.095, and I think that it does. When I put 3.7, let's see, what was the actual number? It was 3.715105758, and I multiplied that by 6 over pi. I got 7.095329346. So I'm going to be happy and call that 7.095. All right, so there we go. I think we've verified what the graph gave us, and then we've shown ourselves that we can also algebraically do this. So what was the question? After how many months will the population of rabbits first reach 150? So we would say 4.905 months after January. And then the second time that it'll occur will be 7.095 months after January. And if we wanted to, we could do the countdown, right? We know that if January is 0, then 1 is February, 2 is March, 3 is April, 4 would be May. So it's looking like it's at the very end of May, almost to June, that we're seeing our first occurrence. I really hope that that helped. We'll be making some more videos that might help you. If you have any suggestions of things you'd like to see, please put your comments below. Thank you.